Hi, I am Mladen Čičić from Gibbs Lab, and I'll talk about our CTEC model and how you can use it for electromobility control. One topic that is getting more and more important is the decarbonization of various sectors of the economy. And the first sector that needs to be decarbonized is probably the power system. The way this is done these days is by introducing an increasing amount of renewable energy sources. However, these new renewable energy sources are posing a bit of a problem to the power system at large. So one problem that they're posing is that at least some of this renewable generation, for example, hydropower generation, tends to be quite remote from the place where we want to spend this energy. And another problem tied to photovoltaics or wind is that these sources tend to be intermittent, which means that we cannot really control when we want them to generate power. So this can be a bit of a problem. Another sector that is becoming more and more important is the transportation sector. And the way this sector is getting decarbonized is through introduction of more and more electric vehicles. Now, from the perspective of the power system, these electric vehicles are also posing some challenges, namely the power demand for their charging is projected to grow quite large and also can come at somewhat strange times. But also, the introduction of electric vehicles has the potential to help the power system quite a lot by potentially acting as a power storage, which is important, especially in case we want to introduce more and more renewables and intermittent sources into the grid. So even today, the transportation and the power network are starting to become coupled in some sense. And this coupling is only going to increase in the future. So I did a bit of a back-of-the-envelope calculation, and it turns out that a 3-lane highway, where if we assume it's operating at capacity and that a quarter of vehicles are EVs, which is, by the way, the situation we have in Norway these days, it turns out that the energy that these vehicles can carry is roughly equivalent to what a 110 kilovolt power line can carry. So I'm not, of course, implying that we should replace power lines by highways, but this is still not an insignificant amount of power from the power system's perspective. So the question that we're asking here is how can we describe and control the interaction between the power system and the transportation system? And the answer that we're offering here is through use of our coupled traffic, energy and charging, or CTEC model. One rather straightforward way to arrive at this model is to first start with a very simple model of an individual EV. And in this case, we're only considering two states. One state is the position of the EV, and the second state is its state of charge. Now, the position of the EV simply evolves according to the velocity of the EV, and we assume here that this velocity will essentially depend on the state of the traffic, which here it is given by the traffic density, rho. And the state of charge of the EV, we're assuming depends according to some function of its velocity. So ideally, we would of course not have to deal with thousands of individual vehicles. Instead, what we want to do is describe this behavior in an aggregated manner, or macroscopically. And of course, if we aggregate the behavior of the EVs when it comes to their motion, we get nothing other than the well-known LWR model. And here we're assuming that the flux function takes a triangular form, just for simplicity. The more complicated part here is how do we describe the state of charge? Now, it turns out that since these vehicles are, in a sense, transporting the state of charge as they travel along the road, that we are able to model the macroscopic dynamics of the state of charge using a transport equation. So what we end up with is an inhomogeneous but linear transport equation, and it is linear because the speed at which this state of charge is being transported does not depend on the state of charge. And the inhomogeneous part essentially takes care of the dynamics of the battery discharge. Now notice that this is a coupled system. However, the coupling only goes one way. So only the traffic density impacts the state of charge. We do not have the coupling the other way. So in a sense, we're assuming that the state of charge does not affect the traffic dynamics. By the way, here we assume, for simplicity, that all vehicles are EVs, but this is an assumption that is not that hard to relax. So this handles essentially the first three letters of the model. We have the coupled traffic and energy. Now all we have to define is the charging part. So charging stations are of particular importance because they essentially serve as the only interface between the traffic and the power system. From the perspective of the traffic, the charging station is nothing other than a pair of on and off ramps. We have some portion of the traffic flow leaving the road, entering the charging station, and then we have some other flow leaving the charging station and entering the road. And of course, these flows will have most likely very different states of charge. From the perspective of the power system, charging station is just a variable demand, a demand that varies in time, depending on how the charging is done and how many vehicles we have at the charging station. Now, if we assume that vehicle-to-grid power transfer is possible, then a charging station can also act as essentially a power storage. There are two important things that we need to take care of when modeling the charging station. The first one is that we want to, at least to some degree, track the state of individual charging vehicles. And there I do not mean to track the state of each individual charging vehicles, but we do want to know the distribution of states of charge. Another thing that we want to ensure is we want to be able to provide different charging rates for different vehicles. And we want to distinguish essentially vehicles according to their state of charge. So the model we end up with for the charging station looks a bit like LWR, but with some crucial differences. So while LWR was describing the evolution of traffic density in time and space, the charging station model describes essentially the evolution of the distribution of vehicles in time and state of charge. So the conserved quantity here is the quantity of vehicles at each state of charge, and you can visualize essentially these vehicles charging as essentially propagating up a state of charge axis. The rate at which this happens, the charging rate, we assume that we can specify it independently for each state of charge. Here's a little example of that. Let's say we have 5 vehicles at 20% state of charge, we have 2 vehicles at 50% state of charge, and we have 4 vehicles at 100% state of charge. And let's say in this case, we want to charge the vehicles that have lower state of charge at twice as fast as the vehicles that have a higher one. After some time, the updated situation would look something like this. So the vehicles that were at 20% are now at 40%, and the vehicles that were at 50% are now at 60%. While, of course, the vehicles that were at 100%, we did not charge them any further, so they're still at 100%. Now, let's say the power system operator requests that we either reduce the power consumption at the charging station, or even that we return some power to the grid. What we can do in this case is we can still continue charging the vehicles that are at 40% and at 60%, but we can try to offset this by discharging the vehicles that were at 100%. What we get after some time is a situation that looks something like this. Now, notice that while we were charging some of the vehicles, the fact that we had 4 vehicles discharging twice as quickly, in this case means that we are on aggregate charging vehicles at a negative rate. And what that means is that the charging station is not taking power from the grid, it is instead returning power to the grid. In this work, we assume that all vehicles at the charging station charge at the same rate, so we do not exploit and control all of these more complicated dynamics. But in a follow-up work that is submitted to IFAC, we did do a bit more complex charging scheme, so keep your eyes peeled for that one. So the full model looks something like this. We have LWR describing the dynamics of the traffic. We have the advection equation describing the dynamics of the state of charge. We have this conservation law describing the state of the vehicles inside a charging station. And of course, we also need to define ramp flows. Here I omit doing that, enough to say that as long as we ensure that the number of vehicles is conserved as they go from the road to the charging station and from the charging station to the road, and the energy is also conserved while they flow to and from the charging station, everything should be still fine. In order to do any kind of control, we would first need to discretize this model. Now, for LWR, the discretization is well known. We simply apply the Godunov scheme and end up with again well-known CTM. For the discretization of the conservation law that describes the charging station, We have a pretty similar situation, except the only difference is that since now the charging rates can also be negative, we also need to take care of that. For the ramp flows, it is again pretty straightforward to transform them into the discretized form. The only part of this model that is not that simple to discretize is the one describing the dynamics of the state of charge. The problem here is that the state of charge, even if we assume that the rate of discharge of the batteries is zero, the state of charge is still not a conserved quantity. So we cannot apply the Godunov scheme in its basic form. So what we can do is, instead of discretizing the state of charge, we can discretize this product of state of charge and density, which is essentially a normalized energy density. And if we're discretizing that, then we can apply a scheme that is very similar to the Godunov scheme. Now, as a part of the Godunov-like scheme, we will of course need to find solutions to Riemann problems at discontinuities at the cell boundaries. And here I'm just showing one small example. And what is shown here is the density on the road, color-coded, with colder being lower density, warmer being higher. And I'm just sketching some sample trajectories of vehicles that would be moving along the road here. And what I'm showing inside of these circles is their state of charge, or the evolution of their state of charge. What you can see essentially is that the vehicles that are inside of the congestion, they are moving slower, so their state of charge will be decreasing slower. Whereas the vehicles that are in free flow, they will be moving faster, and therefore their state of charge will be decreasing faster as well. With this model, we were able to formulate a small control example. We were looking at a ring road with one charging station connected to it, and one pair of on and off ramps that are connecting this ring road to the outside world. And we're using this pair of on and off ramps to essentially introduce some disturbances into the system. For actuation, we were assuming that we control directly the splitting ratio of traffic flow that leaves the road and heads to this charging station. And we assume that we can do this by, for example, adjusting the prices of charging. We had three priorities for control. The first priority was to ensure that the average state of charge of vehicles on the road is always above some minimum value. The second priority is to minimize the maximum number of vehicles that are charging at the same time. And then if these first two priorities are satisfied, then we also wish to regulate the average state of charge on the road to some reference value. In order to achieve these goals, we employ a cascaded control law. And here the inner control loop consists of a gain-scheduled anti-wind-up PI controller, and it controls the splitting ratio to regulate the total number of vehicles charging at the charging station to some reference value. And then we have the outer control loop, which is an anti-wind-up PI controller, and its job is to provide this reference total number of vehicles at the charging station to regulate the average state of charge on the road to the reference value. Additionally, in order to fulfill the first two control goals, we employ dynamic control constraints. And essentially what we are doing is we're ensuring the first control goal by setting the lower bound for the reference total number of vehicles to charge at the charging station. And then we're ensuring the second goal by setting an upper bound for the same reference. Finally, we have some simulation results. Starting from top left and going clockwise, first we have the heat map of traffic density with space on x-axis, time on y-axis. Then we have the situation at the charging station with the state of charge on x-axis and time on y-axis. Then we have the two controlled outputs, so the average state of charge on the road and the total number of charging vehicles given as a function of time. And then finally we have the state of charge on the road in space and time. The vertical blue lines indicate the position of the charging station, and the vertical black lines indicate the on-ramp and off-ramp that connect this ring road to the external world. And to make the control problem more challenging, what we do is during the 5th hour, so from hour 4 to hour 5, we increase the on-ramp flow. And since the on-ramp flow in this case has a state of charge that is significantly lower than the reference state of charge, what that would do is it would reduce the average state of charge on the road. Now, it is, in general, I think, a bit more illustrative to look at the normalized energy, so we would instead look at that instead of looking at state of charge. Here we were comparing two different types of control. The first control, we did not imply the dynamic constraints that I mentioned. Instead, we achieved all of the priorities by simply tuning the PIDs, and you can see that this control does indeed achieve all of the priorities. However, it does so with quite a high number of vehicles charging at the charging station. Now, as a contrast, in case we do employ the dynamic control constraints, we have an even better situation because in this case the dynamic control constraints are calculated according to a simplified prediction model. And in this case we also assume that we have some precognition of the impending disturbance. So what you can see happening is prior to the disturbance, the number of vehicles charging at the charging station will be increased in order to, in a sense, prepare for this wave of vehicles with low state of charge entering the road. And as a result, this control is able to achieve all control priorities, but it does so with a lower number of concurrently charging vehicles. So you can see the comparison here. As expected, the control law that does use prediction acts preemptively and as a result is able to achieve better results and also expend less control. To conclude, I hope to have shown that the transportation and power system either already are or will be very soon intrinsically coupled, and we will have to think of them as such. Then we have seen that the macroscopic state of charge dynamics can be described by an inhomogeneous advection equation, and also that by controlling the charging stations we can influence both the traffic side and the power systems side. This is an active field of research, and some future and ongoing work include developing a more general and rigorous form of the model in the front tracking transition system model framework, as well as to explore the explicit interactions with the power system. So here we were focusing mostly on the traffic side. In our other work, we do look at the power system side a bit more. And then finally, the ultimate goal is to control the coupled transportation and power system over a wider area. So with that, I would like to thank you for your attention, and if you have any questions, feel free to reach out.